Hello all, welcome to Operations Research 2 course. We continue our discussion on network models. In our previous lectures, we talked about the fundamentals of network models. We learned the basic terminology, we learned the shortest path problems, and we learned the minimal spanning tree problems. And in this lecture, we continue our discussion on maximal flow problems, and we will learn how to formulate maximum flow problems as linear programming formulations. So let's get started. Remember, in our previous lecture, we learned about a cut. We said that a cut in a maximum flow model is the set of arcs that disconnect the source from the sink. So in this example problem, we said that we want to send the maximum amount of flow from this node 1, which is source, to the sink, which is node 5. And the set of arcs that disconnect node 1 from node 5 will be a cut. And there are many different alternatives. In this example, cut 1, if we define cut 1 as this set, this arc, and this arc, okay? If we delete these arcs from the diagram, from the network, we see that node 1 is disconnected from 5. Similarly, in cut 2, if we disconnect this arc, if we delete this arc, this one, and this one, again we disconnect node 1 from node 5. Finally, cut 3 is defined as these 3 arcs. When we delete these 3 arcs, we disconnect. But these are not all of them. There are many others. Okay, you can, for example, disconnect, delete this arc, this one, and this one, so that again you disconnect 1 from 5. So there are a lot of alternatives. But in this example, let's consider these 3 cuts. And we learned that in our previous lecture, the maximum flow that we can send from a source to a sink in a network is equal to the minimum cut, the capacity of the arcs in the arc. If we take the minimum of these, then the maximum flow will be equal to this minimum cut. That's why the cuts are important for us. So now, if we want to find the capacities of these arcs, we just need to add up the capacities of the arcs in the cuts. Okay, so in first cut, for example, we have this arc with a capacity of 10, this arc with a capacity of 30, and this arc with a capacity of 20. So for this cut 1, the capacity of the cut 1 is equal to the summation of these, which will be 60. Similarly, we can calculate for cut 2 and cut 3, we can calculate the capacities. And as you can see, in cut 1, we have arc 1, 2. Remember, we represent the arcs with the nodes, okay? 1, 2 is this arc, okay? Node 1 to node 2. And 1, 3, which is node 1 to node 3, and 1, 4 is this one. So cut 1 includes these 3 arcs, and the total capacity is 60. Cut 2 includes these 4 arcs, and when we add up their capacities, we find that the total capacity of cut 2 is 110, and for cut 3, it's 70. So calculating these capacities of the cuts is equal to summing the capacities of the arcs which are involved in that cut. Now, when we calculate these capacities of the cuts for this example, can we answer the question, what is the maximum flow in the network? We know that the maximum flow is equal to the minimum cut. And when you just look at these, the minimum cut is 60. So is maximum flow equal to this 60? Actually, no. In in this example, we just considered 3 cuts, but there are many other alternatives that we haven't considered, we haven't written here. There are cut 4, cut 5, there are other cuts. In order to say that, in order to find the maximum flow, you need to consider all possible cuts, find their capacities, and find the minimum of them. In this case, you can say that the maximum flow will be equal to that minimum capacity. If you just consider only a subset of the cuts, not all, but a subset, and then take the minimum of them, all you can say is this maximum flow will be less than or equal to 60, because we don't know if the minimum cut is 60. Maybe there are some other cuts with smaller capacities. Okay, so maximum flow can be 60, can be less than 60, but all we know is it is not larger than 60, it's not greater than 60. Okay, so maximum flow is equal to the minimum cut, but you need to consider all possible cuts to find that minimum cut. Now, the important thing is we will not, in this course, in this lecture, we will not learn how to solve max flow problems. Actually, there are algorithms, for example, Ford-Fulkerson algorithm that solves the maximum flow problems, but we will not learn it in this course. But we will formulate this maximum flow problem as a linear programming formulation so that you can solve it using any solver like Cplex. Okay, so, and this is an important class of formulations. Formulating network flow problems is very important. Therefore, learning this maximum flow model, and later on we will learn how to formulate minimum cost network flow problems, which is very similar to this one. And these are very important type of formulations, and they are very similar to each other. And after this, we will also formulate the shortest path problem as a linear programming formulation, similar to this maximum flow model. Okay, so the definition of the decision variable is always the same, is very similar. And in order to define the decision variables, you should think about, okay, in this problem, what we are trying to decide on, what we are trying to decide on to maximize the flow. And the answer is we want to decide on the amount of flow in each arc. Okay, so if we represent by xij as the amount of flow, so we have node I and we have node j, and there is an arc connecting this one, and we will represent the amount of flow from I to j with this decision variable xij. Okay, and we know that this arc has a capacity Cij. Okay, so if this is our decision variables, now our objective is to maximize the flow. Okay, so the model will tell us all the flows on all arcs of the network, and somehow we need to find the maximum flow, because look, this is the source and there are some arcs connecting this source to other nodes, and then there are some arcs that connect to the sink node or termination node. Okay, usually we represent the source with S and the sink node with T. And the thing is, we want to find the maximum flow that we can send from the source to the sink, and we can use any one of these arcs in between. And if we know the amount of flow here, if we know the amount of flow here, if we know the amount of flow here, if we know all these flows, how can we calculate the maximum flow? Okay, the idea, how can we find the maximum flow? The thing is, we will consider all the arcs that are connected or that are outgoing from the source. And if we add up these values, okay, the amount of flow that are outgoing, that's outgoing from the source to all others, this will be the amount of flow that is reaching to this termination node also. And we want to maximize this amount, okay? And this is our objective. And what are the constraints of this problem? Simply, in maximum flow problems, there are two constraints. The first one is the node balance constraints, okay, or flow balance constraints. Flow balance constraints. And what are these flow balance constraints? At each node, the input flow must be equal to the output flow. So consider this node I, it's connected to some other nodes, so some amount of flow is being into this node I, and this all amount should be transferred to other nodes. So all inflow must be equal to the outflow, otherwise, for example, the inflow value is 100 and total outflow is 80. What will happen to this difference? 20 units of difference. What will it be? So it cannot be stored, it cannot be used in this node I. It means that it is infeasible to have 100 inflow but 80 outflow. So whatever inflow is, the outflow should be the same. Okay? The only exception to this is the source and sink nodes. For these nodes, we will not have inflow will be equal to the outflow, because the source, as you can see, it doesn't have any inflow, incoming arcs. And similarly, this the sink node doesn't have any outgoing arcs. Okay, so for this example that we considered, the source node is node 1 and the sink node is node 5. This is given in the question. We are not assuming it. It's given in the question. So for this problem, let's formulate this example as a linear programming formulation. So we will define the decision variables. We will define the objective function. We will write the flow balance constraints. By the way, there is another constraint that we need to consider. So what is this value over here? It is the capacity of arc 1,4. Okay, this is the capacity. So the amount of flow in this arc will be represented by x14, which is the decision variable of the LP model. And if this x14 is 20, what does it mean? 20 units is flowing on this arc. But this 10 says that the capacity is 10. You cannot send more than 10 units. So it means that this x14 should be less than or equal to 10. It cannot be greater than or greater than 10. So together with this flow balance constraint, we need also this arc capacity constraints. Okay, so in maximum flow problems, simply we have these two constraints together with the objective functions. So let's define the decision variables corresponding to this problem and also write the objective function and write all these constraints. So the decision variables, first of all, the decision variables are defined as xij, right? Amount of flow. So it means that we have x14 as a decision variable, x13, x12, and then we have x25 and x23, okay? And also we have x45, another decision variable, we have x43 and x34 and x35. Okay, look, we have decision variable x14. We can also define decision variable x41, because as you can see, these arcs over here are not directed arcs. But the thing is, when you look at the capacity that can flow from 4 to 1, it is 0. It means that this x41 is less than or equal to 0, and it means that no flow can pass from 4 to 1. There can be no flow from 4 to 1. Therefore, you don't need to define it. But if you look at this arc over here, as you can see, from 4 to 3, the capacity is 5 units, and from 3 to 4, the capacity is 10 units. It means that the flow can be from 3 to 4 or 4 to 3, depending on these capacities, and therefore we need to define both of them, 3, 4 and 4, 3. But for all others, since there is the other capacity, the return capacity is 0, we don't need to define those decision variables. So the decision variables that we define for this problem are these. Then, how can we write the objective function? And as I told you, the objective function is the total amount that we can send from the source, which is node 1, to the sink, and we want to maximize it. And to do this, we need to look at all outgoing arcs from the source one. And these outgoing arcs are x12 plus x13 plus x14. Okay? So this is the amount of outflow from node 1. And if this amount, for example, 100 units, is flowing out from node 1, and this 100 unit will reach to node 5, which is the destination, which is the sink node. Okay, so we are sure if this 100 units flows out of node 1, it will reach to node 5 because we will write the necessary constraints for this. But on the other hand, this is the amount of outflow from the source node. And as we said, this should be equal to the amount of flow that will reach to the sink node. So we can consider the arcs that are connected to the sink node, which are x45, x25, and x35. Okay, so the total amount of flow on these three arcs are the inflow into the sink node. And this is also equivalent to the total amount of outflow from the source node. So we can write the objective function in two different ways. We can consider the source node and write the objective function as all outflow from the source node, or we can consider the terminal node or sink node. Sometimes we call it sink node. And by the way, sink node is not S, it is T. And we can say that the objective is to maximize the total inflow into the sink node, which is represented by these three arcs. Okay, so our objective will be the maximization of either this Z1. We will not write both of them at the same time. We will write only one of them. And when you write one of them, you will get exactly the same result. Okay, either maximize this Z1, which is equal to this, or maximize Z2, which is equal to this. And let me write maximize, let's say Z1 equal to x12 plus x13 plus x14. I will write only one of them now. And subject to, let's write the constraints. We said that other than node 1, which is the source node, and node 5, which is the sink or terminal node, for all other nodes, the inflow should be equal to the outflow. So we will consider each node one by one. Let's consider node number 2. Okay, node number 2. What is the inflow into node number 2? Look, this is x12, the amount of flow from 1 to 2. No flow can come in this arc in this direction because the capacity is 0. And again, no inflow can come into node from this arc because the capacity is 0. Therefore, the only inflow into this node arc can be through arc x12, so this inflow x12 should be equal to the outflow. And now let's consider the outflow. The outflow on this arc, can it be, for example, x21? Since this capacity is 0, x21 will be 0, no outflow on this arc. But it can be on this and on these arcs. And it means that the inflow should be equal to outflow x25 plus x23. This arc plus this arc. And for node 2, this is the constraint for node 2. We need to write the constraints, such constraints for all nodes. And you can represent this constraint in a different way, because you know in linear programming we usually write all decision variables on the left hand side and all constants to the right hand side. And instead of writing it in this way, we can represent it as x12 minus x25 minus x23 equal to 0. Okay, this is another way of representing. Both of them are correct. Both of them are correct and will provide the same result, will give the same solution. Okay, this is for node 2. Now let's consider node 3 and write the flow balance constraints for node 3. We need to write this for all constraints, for all nodes, remember. Node 3. What are the inflow into node 3? It can be through this arc and through this arc and through this arc. Look, this has a positive capacity. So it can be through this arc, but it cannot be through this one because the capacity is 0. Okay, so now what is the total inflow? Let me write in this way: x13 plus x23 plus x43. This is the inflow, and this should be equal to the outflow. Now let's consider the outflow. Can this outflow be through this arc? No, the capacity is 0. And it cannot be through this one because the capacity is 0. It can be through this one or through this one. So it can be x34 plus x35. Okay, inflow equal to outflow. And similar to the previous one, we can represent it by collecting all decision variables on the left hand side: x13 plus x23 plus x43 minus x34 minus x25 equals to 0. And we need to write the flow balance constraint one more time for node number 4. Okay, node 4. And the inflow into node 4, it can be through this one or through this one, but it cannot be through this one because the capacity is 0. So it can be x14 plus x34, and we should write it equal to the amount of outflow from node 4, and the outflow cannot be to this one. It can be to this one or to this one. So it will be x43 plus x45. And as we collect everything on the left hand side, x34 minus x43 minus x45 equals to 0. Okay, so these three constraints written for all the nodes except the source one and the sink one are the flow balance constraints. Okay, these are flow balance constraints. And what about the other constraint, which is the arc capacity constraint? And the arc capacity constraint says that the amount of flow on each arc should be less than or equal to the capacity of the arc. Now let's consider this decision variable x12, the amount of flow, x14, the amount of flow on arc 14, and the capacity is 10. So it means that this x14 should be less than or equal to 10. It cannot be more than 10 units. Similarly, this one, the flow on arc x13 should be less than or equal to 30, x12 should be less than or equal to 20, we don't need to write x21 less than or equal to 0 because we didn't use this x21 at all. If you write it is not wrong, it's correct. But you don't need to write it because we never used this x21 at all in this formulation. So we continue with the others. x23 is less than or equal to 40. x25 is less than or equal to 30. Then x34 is less than or equal to 10, x35 is less than or equal to 20, and x45 less than or equal to 20. Okay, so these are the arc capacity constraints. And one final thing, which is the sign restrictions. Xij should be greater than or equal to 0 for all I and j. This is the sign restriction. And this is the model. We have this objective function, subject to flow balance constraints written for all nodes, and arc capacity constraints which are written for all arcs, and the sign restriction. This is the LP formulation for the maximum flow problem. We can represent this formulation in a table in a simple way. How do we do it? So we construct a table by writing a row for the objective. Actually, these are alternatives. These are same objectives. So you can allocate 2 lines to write the alternative objective functions. Remember, this Z1 considers the amount of outflow in the source, and Z2 considers the amount of inflow into the sink node. And then for each node other than the source and sink, for each node we allocate 1 row, and the last one is the capacity of the arc. And then we allocate a column for each arc. So this represents arc 1, 2. This represents 1, 3, 1, 4, 2, 3, 2, 5, 3, 4, 3, 5, 4, 3, and 4, 5. These are the columns representing the arcs. And this final last one is the right-hand side of the constraints. So remember, our objective function was maximize the outflow from node 1, and we said that we can represent it as Z1 equal to x12 plus 13 plus 14, the outflow from node 1. Okay. And also we said that we can represent this as the inflow into node 5, and the inflow into node 5 was coming from arc 2, 5, 3, 5, and 4, 5. So instead of writing this in this way, what we can do, we can say that, okay, this column represents x12. Okay, so this is x12, arc 1, 2, and since in this objective function we have x12, we put a 1 here because its coefficient here is 1. And then for 1, 3, again we have a coefficient of 1, we write it here. For 1, 4, its coefficient is 1. What about x23? There's no x23 here. It means that 0 times x23. So the coefficient is 0, and when the coefficient is 0, we don't write it. Similarly, all these decision variables does not appear in this objective function. If you write the alternative objective function by considering inflow into the terminal node, then this time, look, I need to put a 1 to this 2, 5, another 1 to 3, 5, and another 1 to 4, 5. And from this row over here, by just looking at to this row, I can write the objective function, which is maximize Z2, which is equal to 1 times x25 plus 1 times x35 plus 1 times x45. This is the objective function. And we write the constraints similarly, in a similar way. Remember, in the formulation, LP formulation we just developed, we have written a constraint for each node. And the constraint for node 2 was like this. x12 was equal to x23 plus x25. Okay, inflow should be equal to outflow. But when we move this right hand side to the left hand side, we obtain this. It is the same constraint. And now we will write this constraint in the table as it is. So the coefficient of x12 in this constraint is 1. The coefficient of x21 is -1. And the coefficient of 25 is -1. So we will write it here. 1 times x12 minus 1 times x23 and minus 1 times x25. And the right hand side is 0. Okay. Simply this table shows us the formulation. And for node 3 we write the same thing. We do the same thing. The constraint was x13 plus x23, the inflow, minus outflow 3, 4, 3, 5, and there's another inflow here which is x43. Okay, it should be equal to the outflow. Okay, then what we do, we put 1 to x43, 1 to x13, and 1 to x23, and then -1 to x34 and x35, and the right hand side is 0. We do the same thing for node 4. Okay, and then we have our capacity constraints, which is very easy. For all arcs, the amount of flow must be less than or equal to its capacity. And if we just write the capacity to this last row, we say that x12 should be less than or equal to 20. x13 should be less than or equal to 30. Okay, so the capacities are written here. So when you look at just this table, you can easily construct the LP formulation. So we don't need to write specifically the objective function and the constraints, but when we just construct this table, the model is here. Now the question is, how we will solve this model? And as I told you, in this course we will not learn the Fulkerson algorithm. There are algorithms that solve the maximum flow problems. In this course, we will solve such problems using a solver, commercial solver, like the Cplex OPL. And when you use Cplex OPL to solve this problem, we see that the amount of flow from arc 1-2 is 20, 1-3 is 30, 1-4 is 10, and etc. And the maximum flow is equal to 60. So look, this source was 1, and then the flow to 2 is equal to 20, flow to 3 is equal to 30, and flow to 4 is equal to 10 from these. Then from 2 to 5, 5 is here, 2 to 5 is 20, 3 to 4 is 10, 3 to 5 is 20, and 4 to 5 is 20. This is the solution. And look, what's the amount outflow from node 1? 10 plus 30 plus 20, which is 60. What is the inflow into node 5? 20 plus 10 plus 20, it's also 60. And at each node, look at node 20. 20 units arrive, 20 units go out. What about 3? 30 units arrive, 10 units go to node 4, and 20 units goes to node 5. So inflow is equal to outflow. And what about node 4? 10 units arrive from node 1 and another 10 units arrive from node 3. In total 20 units arrive and 30 units leave for node 5. Inflow is equal to the outflow. So this is the solution for this example. Now let's solve another example. So we are given this network, and on this network we want to send the maximum flow from node 1 to node 5. Okay, and we want to formulate this as an LP program. Again, when I ask for LP program, you can write this as maximize this and this subject to this and this. But for this maximum flow problems, you don't need to do this. We will not solve the problem in this way, but we will construct the tableau. Okay, we will construct the tableau as in the previous example, and that is the formulation. Okay, then let's do it. By the way, what will be the size of this table? How many rows and how many columns will we have in this tableau? Remember, in order to write our objective, you can allocate 2 columns, okay, for Z1 and Z2 by concentrating on the source or to sink. These are alternatives. Then for each node other than the source and the sink, I need to have a row. So this is for node 2, node 3, and node 4. And then for the capacity of the arcs, I will have another row. So this will be this number of rows. What about the number of columns? I need to have a column for each arc. So this is one arc, which is 1, 2. So I will represent it by x1, 2. Then there is another x1, 3. And then there is another to x1, 5. So there is no x1, 4 in this tableau. As you can see in this network, there is no x1, 4. So I don't have the x1, 4 in the tableau as well. But it is not, these are not all. We also need others. If you look at node 2, we need to have x2, 3, this arc, and then 2, 4, and then 2, 5. So you need to write all of them. Okay, so when we consider all the nodes and arcs, we obtain this tableau. Okay, so for all arcs 1, 2, 1, 3, 1, 5, and etc., we have a column. So we have a row for 2 alternative versions of the objective function, and for the 3 nodes 2, 3, and 4, and for the capacities, and we have one more column for the right hand side. And remember, the right hand side of the constraints is always equal to 0, 0, and 0. You can simply fill in this table. What is Z1? Z1 is the outflow from node 1, which is, look, this arc, which is x1, 3, this arc, which is x1, 5, and this arc, which is x1, 2. So x1, 2 is 1, x1, 3 is 1, and x1, 5 is 1 in the first alternative of the objective function. What about the objective function, second objective function, which is the inflow into node 5? It can be this one, this one, this one, and this one. So as you can see, it is x1, 5, this one, x2, 5, this one, x3, 5, this one, and x4, 5, this one. So these are the 2 alternatives of the objective function. We will use any one of them in Cplex, for example, while solving. Now I need to write the flow balance constraints for node 2. I need to write the inflow minus outflow. So inflow, first thing, x1, 2, inflow will be positive. Okay, outflow will be negative. So inflow x1, 2, so this x1, 2 will be positive. What else? This can be an inflow because the capacity is 10. So x3, 2. 2 is also positive. This cannot be positive because the capacity is 0, but this can be positive. It can be an inflow because the capacity is positive. So X42 is also 1. These are all possible inflows into node 2. What about the outflows from node 2? Let's consider the outflows. This cannot be an outflow, this one, because capacity is 0. This can be an outflow, which is X23, so outflow will be -1. This can be an outflow because the capacity is 6, X25 is -1, and this can be an outflow, which is X24, it's also negative, and the right hand side will be 0. I will repeat the same thing for node 3. So for node 3, the inflow, let's consider the inflow, it can be X13, this one. It can be X23, this arc, X23. It can be X43 because the capacity is 7, X43. It cannot be X53. These are the all possible inflow into node 3. What about the outflow? It cannot be 131 because this is 0. It can be 32, so it is -1. 34, because the capacity is this one, it is -1, and it can be 35, so it's also -1. So this is for node 3. What about node 4? For node 4, the inflow can be this one, 24. It can be this one, which is 34. It cannot be 54. And the outflow can be, look, 42 can be outflow, so it's -1. It can be 43, and it can be 45. Okay, so these are the flow balance constraints. What about the arc capacity constraints? The arc capacity constraints, for each arc, I need to write its capacity. The capacity of arc 1, 2, I need to look at this side. Remember, 1, 2 capacity is this one. This is the capacity for 2, 1. Okay, not 1, 2. So for 1, 2, capacity is 8. For 1, 3, capacity is 14. 1, 5, capacity is 4. 2, 3, the capacity is 5. 2, 4, capacity is 7. And 2, 5, capacity is 6. 3, 2, capacity is 10. 3, 4, it is 9. And 3, 5, it is 10. 4, 2, it is 6. 4, 3, it is 7. And 4, 5, it is 5. And this is the formulation. You don't need to write the formulation in open form, but if you like, by just looking at this table, you can quickly convert it to a linear programming formulation in this format. And in this table, since all xij are greater than or equal to 0, we don't need to write it at all. So in this lecture, we learned how to formulate maximal flow problems as linear programming formulations, and we reviewed that the maximum flow is equal to the minimum cut that disconnects the source node from the sink node. In our following lectures, we will learn how to formulate minimum cost network flow problems, and also we will learn how to formulate shortest path problems similar to these maximum flow models.